Hello students, good morning. Welcome to our first course in microeconometrics method. And today we're going to do a review of OLS regression. So the materials that you guys are going to learn today are going to be based on chapter 2 till chapter 4 of Jeffrey Woolridge Introductory Econometrics. And we're going to do a brief discussion on PKH, Program Keluarga Harapan. And this is going to be based on a paper entitled Cumulative Impacts of Conditional Cash Transfer Programs, Experimental Evidence from Indonesia by Nur Cahyadi, Remahana, Ben Olken, Rizal Adi Prima, Ellen Satriawan, and Eki Syamsul Hakim. So let's go and discuss it. So the Indonesian program, the Indonesian government implements Program Keluarga Harapan or PKH, a conditional cash transfer program for the poorest 10%. So PKH is actually inspired by successful conditional cash transfer program around the world, which was first initiated by the government of Mexico. It was entitled the Progresa program. So PKH aims to relax poor households' budget constraints so that they can spend more for their children. And the goal of PKH is to improve health and educational outcomes of children from poor households. Now, of course, with any programs, the government wants to do evaluation whether or not the program is effective. Okay, because they're spending a lot of budget, they're spending a lot of money, and they want to make sure that it actually changes the outcomes that they're looking for. So the government wants to do an estimation on the effect or the impact of PKH on indexed children's height using WHO's height for age metric. So using administrative and survey data, a researcher writes the following econometric specification. So height subscript I equals beta 0 plus beta 1 PKH subscript I plus U of I. Now PKH is a binary variable which indicates 1 if the household I receives PKH and 0 otherwise. So there are questions that you guys should be able to answer given foundations that you get from introductory econometrics. So the first question, which we actually provide you a hint of, what does I denote? And what are beta 0 and beta 1? And what is the expected sign of beta 1 and why? And what is the interpretation of beta 1? The next two questions that we're going to answer, which is also important in microeconometrics and econometrics in general, is that first, when is it possible to recover beta 0 and beta 1 from the data? And how can we actually do it? So let's go through the first question. When is it possible to recover the parameters from the data? So beta 0 and beta 1 are population parameters, so they're not statistics. And in many cases that we're going to deal with, population parameters values are actually unknown. So we don't know their values. And so what can we do? Well, you need to obtain a sample, and using the sample, you can estimate beta 0 hat and beta 1 hat. So beta 0 hat and beta 1 hat are statistics, and they are estimates for the population parameters who's unknown. So the question is, what is the criterion for the sample for the estimation? Okay, and what is the main assumption such that we obtained an unbiased estimate of beta 0 and beta 1? Okay, so let's go through the main assumption in linear regression model. So you can remember assumption 1, assumption 2, assumption 3, and so on. But here I'm going to ask you guys to focus on one assumption. So the key assumption involves the conditional expectation of U given PKH, or we usually write it E of U conditional on PKH. Here we're going to assume 0 conditional mean assumption. Expected U of PKH is equal to 0. What does it mean? This assumption implies that U, the unobservable, and PKH are not correlated. So since the key assumption involves an unobservable variable, it cannot be tested. So what does this assumption says? It says that on average, the unobservable characteristics of those who receive PKH are going to be the same with the unobservable characteristics of those who receive PKH. Well, I'm going to let you guys do the thinking and whether or not this assumption makes sense or not. So given this assumption, the expected value of the statistics beta 1 hat is going to be equal to the population parameter beta 1. So in other words, if we fulfill the zero conditional mean assumption, beta 1 hat is going to be an unbiased estimate of beta 1. The zero conditional mean assumption is also referred to as the exogeneity assumption. So this is something that you're going to hear over and over again, whether or not a variable is exogenous or a variable is actually the opposite, endogenous. So going back through the assumption on zero conditional mean assumption, we can ask, well, is the assumption sensible? Can you think of an example such that the assumption fails? Can you think of an example why on average, individuals who receive PKH are quite different with those who do not receive PKH, particularly on the unobservables? Now let's take one example. Suppose that one unobservable variable in U is household food expenditures. What does the zero conditional mean assumption imply in this case? And does the zero conditional mean assumption hold in this case? Okay, well, suppose that now the expected value of U conditional on PKH is actually not zero. It means that there is a correlation between factors that we do not observe in U and PKH. Well, if this is the case, then the expected value of beta 1 hat is not going to be equal to beta 1. In other words, the estimated coefficient is going to be a biased estimate of the parameter. Now, this is going to be called the omitted variable bias because there are unobservable variable that is correlated with both the outcome variable, height in this case, as well as whether or not a household receives PKH. In other words, PKH is not exogenous. Well, this is quite straightforward because PKH here is going to be endogenous. And so we're going to be dealing with endogeneity issue. Now, please note that endogeneity issue is not specifically due to omitted variable bias. Omitted variable bias is just one issue that could do endogeneity bias. So, how big is the bias? That's another question that we need to think. Well, the bias of beta 1 hat is going to be the difference between the expected value of beta 1 hat and the true value of the parameter beta 1. Now, the bias is going to be beta 2 multiplied by delta 1 tilde. Now, you're going to be asking questions, what are beta 2 and delta 1? Well, beta 2 is actually the relationship between the omitted variable and the outcome of interest beta 2. So if you can think of household food expenditure is going to be the unobserved variable. So beta 2 is going to be the relationship between the height and the unobserved household food expenditure. Now, delta 1 is the relationship between the explanatory variable of interest, in this case is PKH, and household food expenditure. So you guys now can think that the bias could be positive or the bias could be negative. It really depends on the values of beta 2 and delta 1. So if suppose that both beta 2 and delta 1 are positive, then the bias is going to be positive. And if beta 2 and delta 1 are both negative, the bias is going to be positive. However, if one of the parameter is positive and the other one is negative, then the bias is going to be negative. Okay, so this is going to be an overview on the bias that we can obtain, conditional on the value of beta 2 as well as the correlation between the variable of interest and the conditional on the variable of interest as well as on the So this is the graph that maps the bias. So whether or not the bias is positive or negative, it really depends on the value of beta 2 as well as the correlation between the omitted variable and the variable of interest. So how do you overcome the issue of omitted variable bias? Well, maybe perhaps one way that you can think of is the multiple linear regression. So we can use multiple linear regression model to include more explanatory variables in the specification. So specifically, the height of the children equals beta 0 plus beta 1 pKh plus factor x plus factor z and plus unobservable Cu. Now, of course, our main interest is still estimating the impact of pKh on child's height, beta 1. Okay. Now, the question that you need to answer is, what does I and J possibly refer to? And why do we want to model it this way? Well, in this specification, we added two factors of characteristics. The first one is the factor X, which is a factor of child I characteristics, such as age and then gender, whether or not they're the first children, whether or not the children has a chronic condition when he or she was born, and so on. The other factor of characteristics is the household characteristic. So, for example, it's going to be the parents' education, parents' occupation, household expenditure, and particular household food expenditure, the number of dependents in their house, as well as other environment characteristics such as the region in which they live, whether or not they're in the urban or the rural, and so on and so forth. So given the assumption and given the specification, the key assumption is now the following. So the expected value of the unobservable, conditional on pKh, the factor of child characteristics, and the factor of household characteristics is going to be equal to 0. Now, this implies that all vectors in the unobserved error term will be uncorrelated with the explanatory variables. And we also have correctly accounted for the functional relationship between the explain and the explanatory variables. Now, given that we've added variables, are we now more confident of obtaining an unbiased estimate of beta 1? Well, unfortunately, not necessarily. There are still going to be other unobserved variables that are correlated with the outcome of interest, height in this case, and it is also correlated with the program being evaluated, pKh. So you guys should think of an example of such kind of variable that could still be correlated with both height as well as pKh. Well, going back to the discussion, well, children from pKh households are systematically different to children from non-pKh households. In many ways, they are observable and unobservable. So adding control variable, or usually called the covariates, available in the data do not guarantee us to obtain an unbiased estimate of beta 1. So what will be an ideal solution? Well, the ideal solution are going to be things that we're going to learn throughout the semester. It could be the difference in differences model. It could be the instrumental variable. It could be the regression discontinuity design, and it could be the matching. So it really depends on the design of the program and the intervention. And given the design of the intervention, what would be the ideal tools that we're going to use? So going to the second issue that we're going to face when we're dealing with impact evaluation or program estimation is measurement error of x. So omitted variable bias is just one example of endogeneity bias, and endogeneity may also arise from the issues of errors of measurement, particularly on the variable of interest x. So suppose the value of x that you observe is actually not the true value. So the true value that you observe, that you do not observe, is x star, and what you observe is x star plus some random errors. Now suppose one particular example is going to be household expenditure. It's really difficult to say that the observed expenditure in data set, for example Susanna's and then the OLS, reflects the true expenditure. There could be some errors such that we do not observe the true value. So for example, it could be the way that the enumerator asked the question. It could be due to the households not recalling their expenditure in the past week, for example. So there are issues that could lead to measurement error. So this is something that that is quite relevant when we're doing survey data. So suppose that the true model is the following. So y equals to beta 0 plus beta 1 x1 star plus some unobservable variable. So in reality, we can only observe a noisy measurement of x star, which is x, as we've discussed. And we're going to assume that the expected value of the shock or the error term E is equal to 0 with a fixed variance or constant variance of sigma square E. And there is no correlation between the true value of x star, and E. It means that the errors are totally random. So the error is not specific to, say, a subgroup of the population, such as, if we're thinking about a survey data, or the likelihood of getting measurement error is higher among the poor people relative to the non-poor people, all the other way around. So that's not the case. So we're going to assume that the true value and the error is going to be random. And the covariance between the error and the unobservable is going to be 0. So this is called the classical errors in variable, or the CEF. And so the probability limit of beta 1 is going to be equal to beta 1 multiplied by a factor. So the factor itself is a ratio between the variance of the true x divided by the variance of true x plus the variance of the error. Now, if you take a look at the factor, you notice that the value of the factor is always going to be between 0 and 1. And so the estimation of beta 1 is going to be biased by this factor. Now, since the value of the factor is always between 0 and 1, then the estimated beta 1 is going to be close to 0. Now, this is going to be referred to as the attenuation bias, so bias downward. So, I've mentioned two issues of endogeneity. The first one is the omitted variable bias. This is a classic problem. And the second issue is measurement error. So in this microeconometrics course, you will actually learn methods to deal with endogeneity issue. So these methods include difference in differences, or DID, or perhaps we can extend it to triple differences, instrumental variable IV, regression discontinuity design, RDD, and matching. So each case is going to require different estimation method, and there is no tool that fits for all cases. So it really depends on the design of the program. It really depends on the design of the intervention. So we can't really say whether, for this particular program, we always need to use IV, or for this particular program, we're always going to use DID. No, that's not the case. We have to look carefully into the design of the program and whether or not we can find some interesting exogenous variation in the model that we can take advantage. And from there, we're going to choose which tool or which method is actually the most appropriate. The next big topic that we're going to learn in terms of OLS regression is going to be heteroscedasticity. So we're not only interested in obtaining an estimate of beta 1, which is beta 1 hat, but we're also interested in looking at the standard error of the estimated coefficient, which is the standard error of beta 1 hat. So the standard error of beta 1 hat is also referred to as the precision. So the higher the standard error, it means that the precision of the estimate is actually low. But if you have a lower standard error, it means that the precision of your estimate is actually high. Now, recall the homoscedasticity assumption. So the error term has the same variance given any value of the explanatory variable. So the variance of u conditional on x is equal to a fixed or a constant variance sigma square for all x. So it means that for all x that you observe in the data, you're going to assume that the variance of the factors that you don't observe, u, is going to be a constant. So given the OLS assumptions, the variance of the estimate beta 1 hat is going to be equal to the sigma square divided by the variance of x. Now the question is, do we know the value of sigma square? Well, as in the discussion that we had earlier today, sigma square is a population parameter, and it's quite difficult in this particular setting to know the value of the population parameter. So if we don't know the population parameter, what can we do? Well, we do an estimation using the sample that we have. So what we can do is that we can obtain a non-biased estimator, sigma hat square, for the population variance sigma square. So given the OLS assumptions, assumption 1 until assumption 1 until assumption 5, we can actually obtain an unbiased estimate of the standard error of beta 1 hat. So this is going to be a ratio between sigma hat divided by the variance of x. Now, standard error of OLS is also referred to as the precision of the estimate, as we've discussed in several slides back. So given the formula in the previous slide, what factors affect the precision of the OLS estimator? Now, given the factors, you can actually improve the precision of the estimate by adding more observations and adding relevant variable into the regression specification. So if you add relevant variable into the regression specification, then the variance of the residuals are actually going to be lower, and so that's going to lower the standard error as well. Now, by adding more observations, it means that you have bigger n, and bigger n leads to lower standard error. Now, just a very quick note, OLS is still unbiased and consistent under heteroscedasticity. So it's not about the estimate of the parameters, the betas. It's actually about the estimate of the standard error. So heteroscedasticity is, it validates variance formulas for OLS estimators. So the usual F test and T test are not valid under heteroscedasticity. Now, under heteroscedasticity, OLS is no longer the best linear unbiased estimator. There may be more efficient linear estimators, such as the weighted least square estimator or the WLS. Now, the good thing about heteroscedasticity is that there's been numerous development on how to actually obtain heteroscedasticity robust standard error in the past 2 decades or 3 decades, maybe perhaps more. So the formulas for OLS standard errors and related statistics have been developed that are robust to heteroscedasticity of unknown form. Now, this is valid for large samples, and the formula for heteroscedasticity robust are the following. So R square is the squared residual from the regression of xj on all the other independent variable, and SSR squared j is the square of some squared residuals from this regression. So this is a very straightforward formula that you can implement in your regression. Of course, when you're dealing with stata, for example, you can always use the robust option. Now, there are more ways that we can actually use to obtain heteroscedasticity robust standard errors, and it really depends on the design of the data itself. So for example, you're going to learn about cluster standard errors, particularly when you're dealing with panel data where observations for each unit is actually correlated across times. So that's another discussion for the future. So thank you so much for your attention. This is going to be the end of our first lecture on review of OLS regression. I hope you have an opportunity to read the chapter materials as well as go through the main concepts that we discuss in this video, as well as in the quizzes and the problem sets. Thank you and see you in the next lecture.